Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about stoichiometry, which is more or less a way of talking about how we can balance chemical reactions and then make use of these balanced reactions in some approaches that we've actually seen before. So first of all, one of the biggest things when working with chemical reaction is that oftentimes all we know is what our reactants are and what our products are, not how many, not the general chemical formula. More or less what I'm talking about is that dreaded word problem. So for example, somebody may tell you about water splitting. Water can be split into hydrogen and oxygen for energy storage. So this is actually a good way to do green energy storage because water is, well, about as green as it gets. And then you can go ahead and take out hydrogen, which is an energy dense fuel, and oxygen, which is more or less everywhere and is all pretty green. Then you can do the reaction in reverse to generate energy. Now, efficiencies aren't great, but it's a good potential energy storage mechanism for the future. Now, the question is, what does this look like in terms of a chemical reaction? So if I'm going to try and make the reaction, the first thing I'm going to want to do is write down the species and the forms. So water should be in the liquid phase. Hydrogen and oxygen are going to be gases naturally. So this is what we call a skeletal or an unbalanced reaction. Expect to get these a fair bit because this is really when people are talking, this is how they talk. However, in order to actually make use of chemical reactions, we need to know exactly how much hydrogen and how much oxygen is being produced and how much water do I need to make the reaction work. So for that, I need to have a balanced equation. So it turns out in order to have equal number of hydrogens on both sides, and oxygens on both sides, I'm going to need 2 water molecules to produce 2 hydrogen gas molecules and 1 oxygen molecule. 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. Always worth counting the number of atoms on both sides just to make sure that you're good. And these prefactors are known as stoichiometric coefficients. So the idea is that stoichiometry is all about balancing how much I'm consuming and how much I'm producing during a reaction. And these help show the ratios in between the species in the reaction. So for example, I get as many molecules of hydrogen out as I put in molecules of water. However, I only get half as many oxygen molecules out. And this actually is going to be very informative when you're trying to, say, manage a real chemical reaction. Go figure, we want things to be useful. Now, the trick is, how do we actually balance chemical reactions? Well, you can do it through several key steps. So let's go ahead and start with a good general chemical reaction. This is combustion of methane. A little bit less green, but at least CO2 is less of a greenhouse gas than methane is. And this does produce energy. So when we're going to go ahead and do this, the real key is figuring out which elemental species you want to, which chemical species you want to balance first. And a good thing to do is start with the least common elements and then go to the ones that show up in more things. For example, oxygen shows up in 3 different species. That's not a good place to start. Carbon shows up in 2, hydrogen shows up in 2. So we'll probably go ahead and start with one of these. In general, it's also important to balance polyatomics as a unit. This is more or less a fancy way of saying, whatever I write down in my skeletal equation, I'm not allowed to write down any other chemical species. I can't start generating free carbon or producing free hydrogen. Whatever I start with is what I got. So let's go ahead and do this first. So I have 1 carbon on the left, 1 carbon on the right. So I have equal numbers both there. So I'm going to go ahead and tentatively write down a prefactor of 1. Now let's go ahead and do hydrogen. I start off with 4 hydrogens on the left and 2 hydrogens on the right. I need more hydrogens on the right, so let's go ahead and double this number and see what happens. So now I've got 4 and 4. We're balanced. Now, next up, I've got oxygens. This one gets a little bit messy. Got 2, 2, so a total of 4 oxygens on the right, and then 2 on the left. And again, this goes into the last key component. If you have a lone element, you balance them last, in this case. To have 4 oxygens on the left, I'm going to need a prefactor of 2. Now, one of the things I do want to emphasize is this one actually worked fairly simply. A lot of reactions may be an iterative process. For example, you may have to at some point double the number of carbon atoms on the left in order to make everything balanced. Sometimes in order to avoid this, people will multiply by fractions. Say, instead of having to double something on the left, I'll simply put a 3 halves on the right. The important part is that when you end, everything needs to be a whole number. So what you can do is, let's say I've got 1 on the left and 3 halves on the right. You have to multiply everything by 2 just to make sure everything is whole numbered at the end. So good thing to keep in mind. So let's go ahead and see if we can use this to make some predictions. One of the classic things you can do is try and use a balanced chemical reaction in order to relate the amounts of reactants being produced and products. And this is actually going to be very similar to what we did to relating the number of atoms, the mass of atoms in a molecule, because it's going to be all about stoichiometric conversions. So the key thing is always going to be going from grams of whatever to moles of molecular species, because remember, when you're transferring in between 2 chemical species, the only way to do it is relating moles of A to moles of B. In this case, knowing I start with 2 moles of water, ending with 2 moles of hydrogen. So whatever sort of initial amount you're given, first thing you're going to want to do is convert it to moles of your reactant, and then use the stoichiometric ratio to figure out the desired moles of whatever I care about. And then if I'm asking for grams, convert to grams. If I'm asking for volume, convert to volume. Now, again, as always, this feels a little vague and esoteric, so let's work a real problem. So let's try and calculate the amount of aluminum oxide produced if I start with aluminum, essentially metal, and solid iron 3 oxide, and I'm producing liquid iron and aluminum oxide. Now, the first thing we need to do is actually write down the skeletal reaction, and this one's really messy, which all too often they are. So my reactants here are aluminum solid and iron oxide solid. Now, when we balance out the iron oxide, iron 3 oxide, we'll find out that it's Fe2O3. This is traditionally considered rust. And I end up producing aluminum oxide. Aluminum has a +3 charge, oxygen a -2, so it should be Al2O3, and liquid iron. Now, those of you who are on top of this might actually know what reaction this is. This is known as the thermite reaction. This reaction produces great big gobs of heat. If you actually do this reaction on top of a metal engine block, it will melt through the engine block. Feel free to, as long as you're on YouTube, go look that one up afterwards. It's a quite potent, very exothermic, as in it generates a lot of heat reaction. However, the reaction I provided here is unbalanced. I've got 1 aluminum on the left and 2 aluminums on the right. So in order to balance the chemical reaction, let's go ahead and double the amount of aluminum, and we're going to need to do the same thing with iron. Oxygen is already balanced. So we now have a balanced chemical reaction. Always make sure you're using a balanced chemical reaction before you try and do any stoichiometric conversions. So now we need to go ahead and figure out, well, what am I trying to do? So I'm starting with grams of aluminum, and I want to figure out grams of aluminum oxide. So let's go ahead and map this out with unit analysis. Start with grams of aluminum, which I can convert to moles using the molecular weight of aluminum. And then I can use stoichiometry to convert from moles of aluminum to moles of aluminum oxide. And then convert from moles of aluminum oxide to grams of aluminum oxide, always making sure you can cancel out your units as you go, ending up producing units, grams of aluminum oxide. Now, let's go ahead and put in our numbers. We have our 2 molecular weights and a 2-to-1 conversion. So when we do this, it turns out that if I start with about 4.7 grams of aluminum, I'm going to produce about 9 grams of aluminum oxide. Now, this might seem a little weird because I should have a reduction in the moles of aluminum present because I go from 2 to 1. It should half. But here's the important part, that molecular weight, because aluminum oxide is 4 times as heavy. So even though I have half as many moles, the weight quadrupled, meaning that the weight of aluminum is going to be half that of aluminum oxide. So this shows us how we can make numerical predictions using a basic skeletal chemical reaction. Now, we're going to go ahead next time, zoom out a little bit and talk about what different types of chemical reactions are out there and how we can make use of them and where we should expect to look for them. Until then, take care.